We're going to talk now about Chapter 3, Section 7, which is the last section of the chapter, about Bernoulli's principle. So Bernoulli was a Swiss scientist who lived in the 18th century, and he discovered something extremely important about fluid dynamics. So dynamics meaning when a fluid's changing or in motion. And what he discovered was a principle that when you have pressure, the pressure from the side or lateral pressure exerted by a moving fluid decreases as the fluid's speed increases. So if we have a fluid moving slowly, so imagine an airplane wing, for instance, and the airplane's sitting there doing nothing. So there's no motion. Then the pressure is going to be the same everywhere, according to Pascal's principle. Okay? But once this plane starts to move, say it starts to move forward, then you'll have the air streaming by the plane's wing. And the faster this air is moving, or the faster the plane is moving, the lower the pressure gets that's being pushed onto the sides of the wing. That's the Bernoulli's principle. That may not sound like much, but there's many applications of this principle. One of the coolest things that the book talks about is a little experiment you can do at home that I'm going to have all of you all try, because it's quite interesting, is to take a light spoon. A plastic spoon works the best. Go to a nice sink faucet, turn the water on so that there's a nice stream of water. And you can actually vary how much water to see if that makes a difference. But what's really making a difference is the speed the water is moving at. The only way you're going to be able to control the speed of the water is if you can make this opening smaller or bigger. Probably not going to be able to do that easily at home unless you happen to have some kind of a nozzle that you can control from a hose. But you don't need to do that. But I just want you to experience this. It's very interesting. Take a spoon, and if you just stick a spoon into a stream of water like this, we take a spoon, and we just stick it into this stream of water, what force is going to get put on the spoon? Well, we stick it into the water. We know it's going to get pushed down really hard by the water, right? If you just stick it right in the stream. But what will happen if we instead take the spoon, put the spoon this way, so that the back of the spoon just touches the stream of water. And the more dramatic you'll notice this is, the more upright you get the spoon. You might expect to feel like the spoon is being pushed down by the water. But what I want you to do is go try this. And maybe if you don't want to know a spoiler, go try it before you watch the rest of the video. But now I'm going to spoil it for you. What happens is you will feel a force pulling up, almost like a magnet, sucking the spoon. And why? Why does this happen? Well, the spoon will have water as the spoon moves into the flow of the water. We'll have water flowing over the back side of the spoon very quickly. And this quickly flowing water reduces the pressure on this side of the spoon. In other words, the spoon is no longer feeling pressed by the air. So we have Pascal's principle applying everywhere else, pushing of the air, pushing everywhere on the spoon. But the back of the spoon no longer has anything pushing on it. The water is flowing so fast that there's a very small amount of pressure here, which actually causes the forces of air pressure to push up on the spoon. And if the spoon is light enough, like a plastic spoon is very light, you will be able to feel this force from the air quite well. I think that's a really neat application of the Bernoulli principle. Another application that's super important and as a long history with mankind, is flight. As the book points out, mankind has dreamed for years about flying, like the birds. And as we all know, we've discovered ways of doing this, the most interesting of which is the airplane. And how does an airplane work? It works with Bernoulli's principle. And it works by having what's known as an airfoil. You might call it a wing. This is the cross section. Moving with the air flowing at it. I just drew that terribly. Let's try this again. So the air is coming right at it and being pushed to the side by the airfoil. The air is moving fairly quickly. What you might notice is the distance from here to here on this line is less than the lines that are curved. And what this causes to happen is that the air speeds up on these longer lines, and it doesn't speed up on the lower line. So the air actually moves faster as it's pushed here by the wing, and this increase in speed of the air causes this flow on top to move faster than the flow on the bottom, which is moving, we'll just call it normal. Okay, so this flow moves one speed, and the flow up here moves a little faster due to the shape or the geometry of the airfoil. And this higher speed causes there to be a lower pressure due to air pressing down on the wing laterally than the normal speed below. And this smaller amount of pressure versus the larger amount causes there to be a net force pushing up on the wing. We call this force that pushes up on the wing lift. Pretty straightforward name for it. It lifts straight up. Actually, it lifts according to the angle of the plane, or the wing, because it depends on the net imbalance of these forces and the speed at which the air is flowing over. So there's rather complex dynamics, and you can study this in college and at a very high level and become an engineer in aerodynamics and study this sort of thing. It's really complicated. So the airfoil, though, the reason I want to talk about this is there's several forces that act on an airplane, and it's really helpful to have a diagram of this. And the book's diagram is fairly good, but I'm going to give you another viewpoint of this. So an airplane flying has wings, of course, that make it work. So if we imagine an airplane, I'm going to draw my sort of crude version of an airplane. So here's our airplane flying through the air, and it's moving at significant speed. We're going to draw a jet airplane. Okay, so it has these jet engines. The jet engines thrust the airplane forward using gas turbines that burn fuel, turn chemical energy by burning it into kinetic energy, forcing this airplane forward. And we'll talk more about energy next week. But this causes this ejecting of this hot gas due to this chemical reaction causes a force to act on the plane that pushes it forward, called thrust. Okay, so we have, this is the center of gravity of the airplane. We'll imagine the force is acting on that point. So this forward force is called thrust, and it's caused by whatever motive force we give the plane to move forward. In this case, jet engines. And the speed that we achieve in the air then causes lift, and the lifting force is directly proportional to the square of the plane's speed. So speed times speed, or speed squared. So the faster we go, our lift is going to actually go up double, not double, it's going to be that times itself. So if we double our thrust, or not really our thrust, but our speed, which is more complicated than just doubling the thrust. If we double our air speed, we will quadruple our lift because we'll have doubled squared. If we triple our air speed, we will multiply our lift force by 9. Okay, lift can also be increased by designing the plane to have more lift, or by changing the structure of the geometry of the airfoil by using certain structures that we'll talk about in a minute. Basically, let's talk about them now. They're called ailerons, which cause, sorry, not ailerons. The ailerons is another thing that changes the shape, but that's used for turning the plane. Flaps, which can make the wing get bigger this way. So the flaps kind of make the wing get bigger this way by this whole section of wing will come down. I don't know if you've ever been on an airplane, but if you have, you might see this happen during takeoff. And sometimes some planes have slats which come forward. They make the wing get bigger. So you can imagine this piece of the wing here kind of folding down further, and the piece up here folding down further, which makes this speed change even more dramatic and make it even faster above, creating more lift. You can also, the bigger the wing or the more surface area it has also increases the lift. So there's other ways there of creating more lift. So lift is the force that lifts up on the plane and makes it fly, and makes it, it's no longer just like in section 6 we talked about buoyancy. It's not the force of buoyancy lifting up, it's this force due to Bernoulli's principle lifting up the plane and making it fly through the air. So it's not floating, it's actually being lifted up. Now all this motion isn't free. By breaking the air up and squishing it and making it go faster, we're actually creating a force that's dragging on the plane and pulling back on it. We call this pullback force drag. And in order to reduce drag, airplanes are streamlined, which means they use nice, gentle curves and lots of scientific analysis of the dynamics created by these structures through the air motion, the fluid dynamics, to reduce the amount of drag as much as possible, because drag simply reverses the force of thrust. If we have too much drag, we won't be able to keep the plane moving any faster. If we add more thrust and it just adds more drag, they might just cancel out. They might not even move any quicker. And of course, we have the force of gravity pulling down on the plane all the time. And when these forces are at an equilibrium, the plane will be moving at a constant velocity through the sky. If we make lift a little higher, the plane will climb and gain altitude. If we make it lower, it'll begin to go down and descend. If we increase thrust beyond drag, we'll actually begin to accelerate and move faster and faster. If drag increases for some reason, or we lower our thrust, we'll start to move slower and slower through the air. Moving slower through the air then causes the lift to go down, makes the plane lose altitude. Increasing the speed makes the lift go up. So there's kind of this balancing act all the time to keep the plane in the sky. So it's a very complex system to control. And your book goes into more detail about how planes are controlled in the sky to be able to turn them and maneuver them. The main ways that happens, there's 3 kinds of turning in 3 dimensions when you're flying in space, or free, not outer space, but free space, right? The plane is up in the sky, can turn in lots of ways. There's 3 kinds of turning. There is, imagine looking at the plane from the side. So this is the side of the plane. Okay. The plane can roll. Okay. So roll means the plane is rolling one way or the other. turning basically on its axis that goes through the plane the long ways. So if you're sitting on the plane, you'll feel like you're turning right or left. And if the plane rolled, then it would now be oriented this way with the wings, if it rolled this many degrees. A plane can also pitch. So this plane here could pitch up, and pitch is so if it pitched up, it would now be going through this point, and you'd have the tail here and the nose up here, and it would be pointing upwards. And the plane can pitch down, and generally the pitch angle is thought of as being opposite, you might think. Anyway, that's too technical. So there's another one. So this is roll, this is pitch. And there's a third angle that a plane can turn. So if you think about the plane, looking at it from above, so the plane can actually twist like this. And this kind of twisting is called yaw. I don't know if you've ever experienced a plane yaw. It doesn't feel very good. In a boat, you might feel this, or a car that's got rear-wheel drive. When you fishtail, your vehicle starts to yaw. It feels like you're twisting. A lot of carnival rides and like kiddie rides and theme parks you have a lot of yaw in them, like the teacup ride where you are spinning in circles. So there's three kinds of turning in this sort of three-dimensional space. And there's different surfaces in the plane to control each of these. So we can pitch the plane up and down using what's known as the elevator at the back of the plane, which is on this part of the wing here. Not the wing, this part of the tail. If I draw this tail here better. There's a surface here that can be pushed up or down. And usually it's all together usually. So you put the whole thing up or the whole thing down. And if you put it up, that causes the plane to pitch up by Bernoulli's principle. And if you push it down, it causes it to pitch down or nose down. The yaw is controlled by the rudder, which is a similar surface here at the back of the tail that can turn left or right, and that causes the plane to twist. And yaw is useful a couple of ways. When you're doing a turn by rolling, the yaw can help keep the plane's nose pointed in the right direction. And on the ground, when the pilot's driving on the ground, the rudder can be used to turn or to yaw the plane while you're taxiing. And then to roll the plane, the ailerons are used, which are big control surfaces on the wings themselves. And to roll, one aileron is lifted up on one side and the other one's pushed down on the other side. And this causes the plane to roll. And then you null that out or put them back flat in order to stop rolling. And so that's how the plane is controlled. So it's rather complicated, but very, very interesting. And I'm sure we'll have some questions about that flight. And please read the section in your book. Also talks about helicopters and golf balls, curved balls, baseball, and other applications of Bernoulli's principle that we experience in everyday life.